Hello everybody and welcome to my talk on exciting efficient oscillation in nonlinear mechanical systems through Eigenmanifold stabilization. So, over the years, in the past decades in robotics, there have been a lot of interest in mechanical systems that introduced in their physics, in their body, some purposefully designed complement elements or elastic elements. And we call this kind of robots soft robots, either of the continuum side or the articulated side, depending on their inspiration, if these invertebrate animals or vertebrate animals. And the intuition here is that this elasticity should help the robot to perform a series of tasks. And in this talk, I'm particularly interested in those kind of tasks in which it's involved some kind of execution of periodic motions in an efficient and effective way. This is something that we see a lot in the natural counterpart of these systems, where these periodic motions are really produced as an equilibrium between the elastic forces, dynamic equilibrium between the elastic forces and the dynamic forces of our rigid body dynamics. However, when we look at the artificial systems that are multi-body and are immersed in a non-negligible potential field, what we find most often is not regular oscillations, but chaos, or at least pseudo-chaotic and messy behaviors. So what we have been interested into understanding is that if we can extract from this chaos, if we can identify some regularities, some regular oscillations, and how we can use it. And I want to stress here that we are not just talking about any kind of stable oscillation, which would be closer to chaos control, but we want really to find some regular behavior. And in linear system, the well-known model analysis defines a well-specified connection between regular oscillation and normal modes. And we can see here a few examples of mechanical systems either initialized on their modes, so regular oscillation, or in some random part of their or the configuration space, and in that case we observe a messy evolution consistently with the initial oscillation. But of course the real challenge comes with nonlinear systems, and together with Albu-Scheffer we spent some time trying to understand which were the techniques in the state of the art that could be useful in this context. And of course, there is more than 100 years of research here. And we try to organize this research into a coherent framework, which is closer to what we are used to as control engineering in this paper. Very briefly, what we observed is that there is a whole range of definitions, but there is a quite large gap. So the definition goes from very specific symmetry, specific systems with strong symmetries to very general systems with weak symmetries in the definitions. And so we have this very large gap, and mechanical systems that are interesting for nonlinear control, so robots, are exactly in the middle of this large gap. So for this reason, we also introduced a definition of non-Euclidean modes that require some mathematical complexity and gymnastic that we don't have time to do here, and also will not be super interesting. But in a nutshell, the concept is very, very simple. So what we have in the linear case is that all our regular oscillations are collected into space, which is flat, so it's a linear space. So we can use this geometrical concept to describe this infinite collection of regular oscillations that are self-similar. And the idea is just that when we move to the nonlinear case, this space bends, becomes a manifold, but still we can identify these collections of nonlinear oscillations that are embedded into the dynamics of our robotic system. And using this definition, we can look at complex systems like this one here, this double pendulum here with some elasticity, and identify extension of model oscillation of the linear case in strongly nonlinear regimes. And you can see here, for example, for in-phase oscillation, a collection of model oscillations according to our definition. And here just a video of one of these modes for quite high energies. And we have also an anti-phase mode. And really, you can check that paper for more details, but just to motivate you that it's really not just some toy problem that we are solving here. These kind of modes are present in all kind of robotic systems and in all kind of energy level. These are just showing some extreme example just for fun, and also just for fun. These are the 7 nonlinear modes, examples of 7 nonlinear modes that we can obtain if we attach some linear spring in parallel to a KUKA lightweight robot. So this was the definition. It took some time, but hope it pay off. But now that we have this concept, this collection of nonlinear oscillation that we can observe in the form of manifolds in our nonlinear systems, non-Euclidean system, how we can use them for control. And this is the very topic of the paper that we are presenting here. And the concept is actually quite straightforward. So if the system is behaving well when it's on an eigenmanifold and badly when it's outside an eigenmanifold, let's just make the eigenmanifold an attractor of the system by means of feedback control. So we have here a portion of our state space, and we have our initial condition, we have our distance from the manifold defined through this delta, and we want a controller that eventually bring my system to evolve on the manifold according to some regular oscillation. And to this end, we propose a PD-like action. So we have that torque produced by the controller. It's like oriented through the inertia matrix, but then they are defined by a very simple PD rule. So we have here our control gain, and then we have our proportional error and the derivative error. So the complex part probably here to grasp is how this proportional and derivative error are defined. So let's try to look more closely to that. So we have here our eigenmanifold, and we have the tangent space at the equilibrium to the eigenmanifold. If we take a generic point outside the eigenmanifold, x and x dot, we want to define the distance. So the generic point is x dot. What we do is that first we project in a Euclidean manner the point on the eigenspace, so on the tangent space, and we obtain these two xm and xm dot. And then we use these two big X and big X dot functions that I don't have time to discuss here, but they always exist, to map back from the eigenspace to the manifold. And then the difference is going to be this vector here, this distance here between these 2 points. And then in a nutshell, what we do in the paper is that we show that this control action, if we change opportunely the configuration variables of the system, can be written in a much more simpler form, and that extract even more the PD nature of our controller. And then by doing some hypotheses, slowly varying mismatching between the derivative of this guy and this guy here, so more detail are in the paper, of course, we can end up with the dynamics of the distance from the manifold that has this much simpler form. And by taking this gain big enough, we can always make these two matrices negative defined. So therefore achieving stability, at least local stability of the manifold, in the sense of the distance is going to zero asymptotically. So again, more detail into the paper if you're interested. And in the few minutes left, let's just look at how it works on simulation. These are 3 degrees of freedom robot with parallel elasticity, and we just initialize the system outside the manifold, and we stabilize the first eigenmanifold of the system. And you see that after a few seconds, the control action drops to 0 because the system is starting to evolve according to its natural oscillation. And only at the beginning, we have some small transient and this small bump that is produced by this PD controller, but then the system evolves in open loop because it does not need any control action to sustain this natural oscillation. This is a property that, as in general, is not happens for chance. It's a property that this controller always has in general, that once it reaches the steady state, you can also remove it, and the system is going to evolve according to these nonlinear oscillations without the need of any injection of energy. This is the stabilization of the second mode of the same system. And we also tested these things in simulation with real experiments with soft lag. These are not part of the papers, but you can find them online. Other regime of oscillations, and you can also apply the same controller to obtain some more complex behaviors like oscillations in a much higher dimensional system. And again, if you're interested in more details, you can check at the websites that you can find connected to this QR code. That's all. Thank you very much for your attention, and I am happy to answer your questions during the conference, but also later. You can just send me an email to this email address here, or just check my website. Thank you very much.